Hello everyone. Today we're going to learn about the binomial theorem. Now the binomial theorem is used to expand a binomial, so I put here as an example x plus y raised to some exponent, where n, the exponent, is some large number. So rather, let's say if you had x plus y raised to the fifth, instead of doing x plus y times x plus y times x plus y, etc. to 5, there are patterns that we could take note of to kind of make this expansion much easier. So first, we're going to look at the exponents of the binomial, and then we'll look at the coefficients. So the binomial theorem, what that states is that there are patterns to these exponents. So I have here the binomial expansion for when n is either 0, 1, 2, or 3. If you have an exponent of 0, the answer is always 1, because anything raised to an exponent of 0 is 1. Now, if you have an exponent of 1, that's just a plus b. Now, this term goes with this term, and this term is this term. So here, for a, we notice that the exponent is 1. Since there's no b, that means that the exponent would be 0. For b, the exponent of a, since there isn't any, would be 0. But b has an exponent of 1. Now, for a plus y squared, this is supposed to be a b, a plus b squared, that would be a squared plus 2ab plus b squared. Now again, we know these these coefficients, they're going to come into play later, but just take it for now. So this term is this term. This term is this term, and the b squared is this last one here. So right now we're just trying to take note of the exponent. A, as you can see, the exponent is 2. Since there's no b, that means it's 0. For 2ab, both the exponents of a and b are 1 each. For b squared, there is no a, so 0, but the exponent for b is 2. Last one here, we have a plus b cubed. If you were to expand that, you would get a to the third plus 3a squared b plus 3ab squared plus b cubed. So again, this term goes with this term. This one is this one. This is this. And then this final one is this one here. And again, we're just going to note what the exponents are for each term. For a to the third, a has the exponent of 3, and since there's no b, the exponent would be 0. For 3a squared b, the exponent of a is 2, and the exponent of b is 1. For 3ab squared, the exponent of a is 1, and the exponent for b is 2. And lastly, for b cubed, there is no a, so 0, and b cubed has an exponent of 3. So now we're going to look at what is the pattern of the exponents for the first term. If you look, the first term for all of these examples is a. So we start off with here, it starts with 1 and then 0. Then it goes 2, 1, 0. Then it goes 3, 2, 1, 0. What you should notice is that the pattern is that the exponents are decreasing. And it starts with the highest exponent, or rather the exponent of the binomial. Now, if we look at the pattern of the exponents of the second term, here it started with 0 to 1, then 0, 1, 2, then 0, 1, 2, 3. So what you should notice is that the exponents are increasing. But in this case, it is starting with 0. So that would be the pattern of your exponents. All of the first terms would decrease starting with the highest exponent, and all of the exponents of the second term would increase starting with 0. Now, remember here we have these coefficients. How do we get these coefficients if we don't just memorize them? Especially if we're doing a larger binomial expansion. And that is by using what's called Pascal's triangle, named after the mathematician who discovered this. So if you have a binomial where the exponent is 0, obviously that's just equal to 1. If you have a binomial where the exponent is 1, the coefficients are just 1 and 1, as you can see, x plus y to the first. If you have a binomial where the highest exponent is 2, then the coefficients would be 1, 2, 1. And so forth. You can see all of these numbers. These would be the coefficients of all of your terms for a binomial expansion, starting with the exponent of 0 and all the way up to 6. Now you can go as far down as you want. If you have to expand a binomial of x plus y, let's say to the 20th, you can certainly actually continue this pattern. Now how this works and how this Pascal's triangle was come up with, the first and the last number of the triangles, you can see here for every row, it starts and ends with 1. The numbers in between is what you get when you add the numbers right above it. So for example, here, if we start with 1, then 1 plus 1 is 2, and then you end in 1. For this row, we start with 1, 1 plus 2 is 3, 2 plus 1 is 3, end in 1. Next row, start with 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, end in 1, and so on and so forth. So you can continue this pattern as far down as you like. So for example, if I wanted to get the row for x plus y to the 7th, we would start with 1, 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, 20 plus 15 is 35, 15 plus 6 is 21, 6 plus 1 is 7, and then we end in 1. So you get the idea that we're always adding the numbers right above to get the number underneath. So let's say we want to expand x plus 3 to the 4th using the binomial theorem and Pascal's triangle. If you are using, if the highest exponent is 4, then we would actually be using the 5th row, since Pascal's triangle starts with 0. So these would be the coefficients of my expansion. So what I do first is I kind of create a template. I write down my coefficients, so 1, 4, 6, 4, and 1. And I'm leaving space in between for my a's and b's. We know that my first term would start with the highest, so to the 4th, and then work the way down. So this would be a to the 3rd, a squared, a, and then there's none, because it would be a to the 0, and we don't need to write that down. Then my second term, which I'm calling b, starts with 0, so there's no b here, and then it starts increasing. So then this would be b squared, b to the 3rd, and b to the 4th, all of which we would just add. Once you've created your template, you can go ahead and plug in what is a and what is b. So I don't need to write the 1 anymore, so this is x to the 4th plus 4 x to the 3rd times b, which is 3, plus 6 x squared times b squared, plus 4 times x times b, which is 3 to the 3rd, plus b to the 4th. And now we just simplify and work this out. So this is x to the 4th plus 4 times 3, which is 12x to the 3rd, plus 3 squared is 9, 9 times 6 is 54, x squared, plus 3 to the 3rd is 27, and 27 times 4 is 108, x, plus 3 to the 4th is 81. So this would be my binomial expansion. So rather than doing x plus 3 times x plus 3 times x plus 3 times x plus 3 because of the exponent, we actually only use these 3 steps in order to get that expansion. Let's try a couple more examples. Here we have x minus 2y raised to the 3rd power. So I like to label what is a and b. So in this case, a is equal to x and b is equal to negative 2y. So I'm just going to keep that in mind. We will worry about the signs later. So first, let's create our template. This is raised to the 3rd. So I'm going to look at my Pascal's triangle. Since it's to the 3rd, I would be using the coefficients 1, 3, 3, 1. So I'm going to set that up here, 1, 3, 3, 1. My first term, a, starts to the 3rd and then decreases until we get to 0. And then my second term, b, starts with 0 and then increases. Everything is added for now. Now we're going to plug in what is a and what is b. So first we have x to the 3rd, because that's a, plus 3 times x squared times b, which is negative 2y, plus 3 times x times negative 2y squared, plus negative 2y to the 3rd. So now we're going to clean this up. We have the x to the 3rd. 3x squared times negative 2y is negative 6x squared y. Now this negative 2y squared, when you square it, that will give me a positive 4y. So 3x, squared, 3x times 4y squared would be plus 12xy squared. And then this negative 2y to the 3rd, remember you have to apply the exponent to both the negative 2 and the y. Negative 2 to the 3rd is negative 8y to the 3rd. So our final term is negative 8y to the 3rd. There's nothing else to clean up. This is my expansion. So it is a little bit tedious, but it's much easier than multiplying x minus 2y 3 times. And especially with this one, we have 2x plus y raised to the 5th. So now let's see which row of my Pascal's triangle I would need to use. To the 5th, we are using 1, 5, 10, 10, 5, and 1. So that is my row. Our first term starts with the highest exponent and decreases until we get to 0. And then my second term starts with 0 and then increases. And then we add everything in between. In this case, a is equal to 2x and b is equal to y. So now we're just going to substitute everything for a and b. So this is 2x raised to the 5th plus 5 times 2x raised to the 4th, b, which is y, plus 10, 2x raised to the 3rd, b squared, so y squared, plus 10, 2x squared times y to the 3rd, plus 5 times 2x y to the 4th, plus y to the 5th. And now we're going to clean this up. 2 raised to the 5th is 32 x to the 5th, plus 5 times 2x to the 4th. 2 to the 4th is 16 x to the 4th, y, plus 10. 2 to the 3rd is 8, and then x to the 3rd, y squared, plus 10. 2x squared is 4x squared, y to the 3rd, plus 5 times 2x is 10x y to the fourth plus y to the fifth. Now we just need to clean up a couple more of these terms. So we have 32x to the fifth plus 5 times 16 is 80, x to the fourth, y, plus 10 times 8 is 80, x to the third, y squared, plus 10 times 4 is 40, x squared, y to the third, plus 10x, y to the fourth, plus y to the fifth. And this would be my final answer. Now let's look at one more binomial expansion, but in this case with complex numbers. Here we want to expand the binomial 3 minus 2i raised to the fourth power. So in this case, a is equal to 3 and b is equal to negative 2i. Now this is to the fourth, so we're going to need to use the fifth row of the Pascal's triangle. So the 1, 4, 6, 4, and 1, since that's to the fourth. So that I'm going to set up my template here. 1, 4, 6, 4, and 1. My A is going to start to the fourth and then decrease. And then my B starts with 0 and then increases. And adding everything in between. Now I'm going to substitute A and B with 3 and negative 2i. So this is 3 to the fourth plus 4 times 3 to the third times negative 2i plus 6 times 3 squared times negative 2i squared plus 4 times 3 times negative 2i to the third plus negative 2i to the fourth. Now let's clean this up. 3 to the fourth is 81 plus 4 times 3 squared, 3 to the third is 27 times negative 2i. I'll come back here and clean this up more after. Plus 6 times 3 squared, which is 9, times negative 2i, and then all of that is squared, so that would be a positive 4i squared, plus 4 times 3 is 12, times negative 2i to the third. Negative 2 raised to the third is negative 8, and then I to the third, plus negative 2i raised to the fourth. Negative 2 to the fourth is positive 16, I to the fourth. Now we do need to remember our powers of I here in order to simplify this as much as possible. Since our answer for a binomial expansion with a complex number is just going to be another complex number. Whenever you have i's, you should never have an exponent with I, since it all represents either a real number or an imaginary number. So let's see how we can simplify this. We have the 81. Then here we have 4 times 27 times negative 2i, which is negative 216i. Now here we have 6 times 9, which is 54, and then times 4. And remember that I squared is negative 1. So I just separated this 4, and then I replaced I squared with negative 1. Plus 12 times negative 8 is negative 96. So we can write that down now if we'd like, times I to the third. Now remember that I to the third here, let's actually replace that. I to the third, if you remember your powers of I, represents negative I. Plus 16, and then I to the fourth is just 1. So we can leave this as 16. Let's simplify. We have 81 minus 216i. 54 times 4 times negative 1 is negative 216. Negative 96 times negative I is a positive 96I, and then plus 16. 81 minus 216, because now we're going to combine all of the real parts. 81 minus 216 plus 16 is going to equal to negative 119. And then negative 216i plus 96i is negative 120i. So this would be our final answer for this binomial expansion. Now, we're going to continue with the binomial theorem, but instead, now we're going to find what is a particular term of a binomial expression. So what does that mean? If I ask you for, let's say, the fifth term or the third term, I don't need you to expand the entire binomial. I just want to know what is that particular term. And in order to find that term, you need to follow this formula. Now you see a lot of exclamation points. These exclamation points are called factorials. And what a factorial means, like let's say if I were to try to find 5 factorial. This is 5 times 4 times 3 times 2 times 1. So a factorial simply states that you're multiplying the number times every number below that. So 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. 8 factorial is 8 times 7 times 6 times 5, etc. Now what do all these letters mean? Okay, so this is the formula to follow. Obviously, I'm not expecting you to memorize it, but to be able to use it. N is the degree of the binomial, so that is the exponent. R is the term that you're looking for, but minus 1. So if you're looking for the fifth term, R would be 4. Then A is the first term, and B is the second term of your binomial expansion. So let's try that out. If we want to find the fourth term in the expansion 3x plus 2y raised to the 7th, I put here that it may be helpful to create a table with what the values of R, N, A, and B are. So that's exactly what I'm going to start with. I'm going to write down what is all of these letters. So R, I'm looking for the fourth term. So R is 1 less than that, so 3. N is the degree of this binomial, which is 7. A is the first term, so 3x, and B is the second term, which is 2y. So now we're going to use this formula here. So n factorial, that's 7 factorial over r factorial times n minus r, so 7 minus 3, which is 4 factorial. And all of this we're going to multiply by a, which is 3x, raised to the n minus r, so 7 minus 3, which is 4, b, which is 2y, raised to the r, which is 3. And now we got to work this out. So this is my recommendation. We're doing 7 factorial, so that's 7 times 6 times 5 times 4 times 3 times 2. You don't really ever need to write the times 1 because that doesn't really change your numbers. All over 3 factorial is 3 times 2 times 1, so 3 times 2, times 4 factorial, which is 4 times 3 times 2 times 1. All of this, and then 3x to the 4th. So that's going to be 3 to the 4th, which is 81 x to the 4th, times 2y to the 3rd. 2 to the 3rd is 8, y to the 3rd. So now how can we simplify this to make our life a little bit easier? We have here 4, 3, 2, same as in the denominator. Then 3 times 2 is also 6, so I can cancel out this 6. So really, all we have left here is 7 times 5, which is 35, times 81x to the 4th, times 8 y to the third. So now we just need to multiply these numbers together. 35 times 81 times 8 gives me 22,680. And then our variables, x to the fourth, y to the third. And this would be the fourth term in that particular expansion. So instead of having to do the whole thing, you can just apply this formula. Let's try a couple more. For this one, we want to find the fifth term in the expansion 2x plus y raised to the ninth. Now I'm going to write the formula here on top just so that we can use it as a reference. So that's n factorial over r factorial times n minus r factorial times a raised to the n minus r times b to the r. So let's write out what is a, b, n, and r. In this case, a is 2x, b is y, n is the degree, so 9, and r is the term minus 1. I'm looking for the fifth term, so r is 4. So now let's plug everything into this formula. We have 9 factorial, right, because it's n, over r, so 4 factorial, times n minus r, 9 minus 4 is 5 factorial, times a, which is 2x, raised to the n minus r, so 5, times b, which is y, raised to the r, so 4. So now let's work this out one more time. We have 9 factorial, so 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, all over 4 times 3 times 2 times 5 times 4 times 3 times 2. All of this times 2x to the fifth. 2 to the fifth is 32. X to the fifth times y to the fourth. Here I can cancel 5, 4, 3, 2. 3 times 2 here is 6, so I can cancel that as well. And anything else I can simplify, I do. So like here I have an 8 over 4, which 8 divided by 4 is 2. So now here in the numerator is all I have left is 9 times 2 times 7, which is 126, times the 32, x to the fifth, times y to the fourth. 126 times 32 is 4,032, x to the fifth, y to the fourth. So this would be the fifth term in that expansion. Last one here, we have 3x minus y raised to the fifth. Again, I'm going to label. My a is 3x. B is negative y. N is the degree, so 5. And r is the term I'm looking for, minus 1, so 2. So now let's plug everything into the formula. N factorial is 5 factorial over r, so 2 factorial, times n minus r, so 5 minus 2 is 3 factorial, times a, 3x, raised to the n minus r, so 3, times negative y, which is b, raised to the r, so 2. So now let's work this out. This is 5 times 4 times 3 times 2 over 2 times 1, right? But I don't need to write that, times 3 times 2. 3x to the third, 3 to the third is 27, x to the third. And then negative y squared would become a positive y squared. These 3 2's cancel. And additionally, 4 divided by 2 is 2. So what we have here is 5 times 2, so 10, times 27x to the third times y squared, which gives me 270x to the third y squared. And this would be the third term of that binomial expansion. And that's the binomial theorem and Pascal's triangle.